Good morning, everyone. I'm going to present our work dealing with the estimation of the noise emergence of wind turbine noise using a semi-supervised learning method. In many countries, the sound emergence of wind turbine must not exceed regulatory threshold levels. These emergencies are calculated as the difference between the sound pressure level of ambient noise when wind turbines are operating and residual noise, which correspond to all the other sound sources. To ensure to not exceed this threshold, the operation of the wind turbines can be limited by a curtailment plan, which limits the electrical production. However, this residual noise fluctuates over time, which may make the curtailment plan inadequate, with either regulatory thresholds being exceeded or an overly restrictive plan, resulting in more production losses. It is possible to update this plan with residual noise measurement by stopping the machine, but these measurements generate new production losses and remain too punctual to be satisfactory. Consequently, we have proposed a tool to estimate continuously the sound emergence of wind turbine noise. The estimator is based on the extraction of the wind turbine noise from the ambient noise with the help of a sound source separation. With this extracted component, it will be possible to estimate the sound emergence of wind turbine noise, and with this tool, we will be able to adapt the curtailment plan continuously and then to optimize the operation of the wind turbine over time. To perform this source separation, we use the NMF framework with a semi-supervised learning. First, I will introduce the non-negative matrix factorization framework, then I will quickly present the different data used for this experiment, and then I will present the experiment and some results we got. In the audio domain, semi-supervised NMF consists in approximating an amplitude spectrogram of an audio signal, V, by the sum of two matrix products. First, the product WH, where W is called a dictionary composed of K audio spectra or bases, and H is an activation matrix, which represents the temporal variation of each spectrum. Secondly, the products Y, Z with a similar principle, but with a reduced dimension J. Semi-supervised learning will therefore consist in considering labeled data in W, in our case wind turbine noise spectra, as it is the most easily identified source. These data are fixed for each spectrogram. The H, Y, and Z are then the unknowns to estimate for each scene. Consequently, the product Y, Z are free to be adapted to each scene and will thus be able to model the residual noise. To do so, this approximation is done by minimizing a cost function which is expressed as the beta divergence between V and V tilde. An iteration process makes it possible to converge to a solution with update algorithm that change the shape of H, Y, and Z, which depend on the choice of the beta divergences. We also had a regularization term expressed on H, which is a temporal regularity constraint. This term will constrain the update in H to have a smoother shape in order to better correspond to the temporal evolution of the wind turbine noise, which stay quite constant over time. And finally, to estimate the sound emergence with semi-supervised learning, we can either deduce the residual component from the ambient noise and the estimated wind turbine noise with WH, or directly consider the product YZ as the residual noise. Now the data. For NMF, we collected wind turbine noise measurement at a wind farm in France. These measurements were made according to the IEC standard protocol during stop and start measurement. Instead of considering all the 1,000 collected spectra, we reduced their dimension using a K-means algorithm to a few elements to avoid redundant information, but also to reduce computation time. For the purpose of ambient noise measurement, instead of considering in situ measurements, we decided to simulate them in order to have a better control of their composition. The simulation process allows us to know the exact sound emergence, which is not possible in practice. To do so, we collected measurements made on the same wind farm but at 300 meters from the wind turbines, with the most emergent period as possible. And the residual noise is captured on different wind farm locations during the shutdown of the machine. The construction of the scenes is done as following. First, we select a wind turbine noise sample of 10 minutes. And to obtain convincing ambient scenes, the wind turbine noise is filtered by attenuation filter estimated with parabolic equation. The idea is to consider a downwind propagation condition and to simulate accurately the propagation of the wind turbine noise at 500, 1000 and 1500 meters. A residual noise is also considered and is summed to the propagated wind turbine noise to generate the ambient noise. The sum is done by calibrating the residual noise in order to follow an indicator, the signal to residual ratio SRR. It is the difference between the wind turbine noise and the residual noise too. This indicator is defined from -9 to 9 dBA. For this study, we designed 60 scenes, 10 minutes long with a 1 second step. All data are expressed in Pascal in a third octave bands between 20 Hz and 10 kHz. The experiment now. To summarize, we have the NMF part with thousands of wind turbine noise spectra reduced by the Kamin algorithm to obtain the dictionary W. We test several settings, the beta divergences, different dictionary dimension K and J, the weighting of the regression term alpha, and we perform 1000 iterations. Semi-supervised NMF allows the estimation of the sound emergence. It can be estimated either from the product WH or with YZ, the estimated residual noise component. In parallel, we have 60 design scenes, each of them defined for several SRR value and the 3 distances. We also had a pre-processing step, which consists in discarding the most louder temporal frame in the spectrogram and to replace them by interpolated data to assure continuity. And finally, with the emergence estimated by NMF and the exact emergence, we compute an estimation error through the mean absolute error. Bias is also added to help us to interpret the behavior of the method. Instead of summarizing all the results, I only present the optimal combination according to the dimension J and the component considered to estimate the emergence. First, we can see that with an estimation from WH, the best estimation, the value of the dimension J is not significant, meaning that the estimation of the wind turbine component is constant, mainly due to the regularization term that help us to maintain constant its estimation. We can detail for the bold setting in bold letter the bias for each value of the SSR. We can see clearly 2 distinct parts, the first one where NMF overestimates the sound emergence, and a second part where the method underestimates the emergence. We remark that the error increases strongly, especially at SSR equal 9 dBA, where the error exceeds 3 dBA. But when we look the mean absolute error between the exact and the estimated wind turbine noise, we remark that in these cases, this component is correctly estimated with less than 1 dB error. Consequently, the high value of the bias here is due to a higher sensitivity of the emergence than in low SRR. Except this case, the results are satisfying because they do not exceed 2 dBA from -9 to 3 dBA, which is equivalent to a sound emergence of around 5 dBA, superior to the limit of the regulation. With YZ, the dimension J has a higher influence. Naturally, higher G is better the estimation of the emergence because there is more basis to describe the sound source. But with the limited number of dimension J, the residual noise is less well estimated as the residual noise is deduced from the estimated wind turbine noise and the ambient noise. We get a better estimation of the global residual noise and then we get a better emergence. In conclusion, in this presentation, we propose a sound emergence estimator of wind turbine noise based on a source separation method with semi-supervised NMF. To test this method, we use a set of simulated ambient noise. And the experiment carried out allowed to test the capacity of NMF to adapt to the sound source and also to define an optimal setting. We saw that the results were mainly satisfying as they were inferior to 2 dBA for a majority of cases. However, semi-supervised NMF generates over and underestimation depending on the wind turbine noise predominance in the scene. This error is higher when wind turbine noise is predominant due to a higher sensitivity of the emergence indicator than a bad estimation of the wind turbine noise. These results might help us in the future to correct this behavior with, for instance, complementary indicator. And currently, we are considering this method on in situ measurement, showing good and promising results. Thank you for your attention.